When people talk about Logan, they oftentimes bring up the winters. And honestly, yeah, that wind and the snow, it scares some people away. But in my opinion, the worst part is the ice. The ice gets all over the walkways and it's really slippery. And to make matters worse, USU is on top of a hill. So if you live at the bottom of the hill, like me, then you have to walk up the icy slope and risk slipping, which I do a lot. And it made me think, how can I give myself an advantage to not slip? And I wondered, maybe the type of shoe that I wear would make a difference. And that's what this experiment is all about. We're going to measure the coefficient of static friction between the soles of different shoes and an icy surface. Let's see how it works.
We will directly measure two variables over the course of this experiment, the mass of the shoes and the weight attached at the end of the shoes. From that weight attached, we will calculate the mass of that weight, and this mass will be divided by the mass of the shoe to get our coefficient of static friction. Error is introduced with the accuracy of these measurements. The mass of our shoes will have error from the resolution and accuracy of the scale that we use, which has a resolution of 1 gram. And the mass of our weight will be limited by the accuracy of our load cell and load cell amplifier. These are precision errors. When measuring the force of our weight, we will have bias error from the small weight of our bucket and our string, and this will be calibrated for. The impact force of our loading weight and our pulley friction is considered to be negligible. There might also be some drift in our calculated values as the ice melts over time. To minimize these precision errors, we will do more trials, and we also have plenty of ice pans to swap between as the ice begins to melt. We expect our coefficient of static friction values to be greater than 0.01 and less than 0.07 with an error of about plus or minus 0.001. The coefficient of static friction is unitless.
All right, first off, there's no special safety precautions for this experiment. To start, we have an ice sheet and an angle indicator to make sure the ice is flat. We have a weighted shoe on top with a fishing line wrapped around the shoe that's connected to this load cell. And the load cell is connected to an amplifier and the NI-MIDAC, which connects to the digital multimeter, which we can get voltage readings from. And at the other end of the load cell, it goes through a pulley and is connected to our bucket, which we'll fill with water using a siphon pump. And the water in the bucket will pull the shoe, and at the moment of slip, we can look at the voltage reading from the multimeter and determine the weight that caused the shoe to slip.
First off, we will start our voltage capture. Then we will slowly pump water into the bag until the shoe slips. Once the shoe slips, we can analyze the voltage capture to figure out the exact moment the shoe slipped. A few gaps in the trial experiment we noticed that will be monitored are maintaining a consistent ice surface, as uneven or melting ice can affect friction measurements. To address this, we will ensure a uniform freeze and refreeze between trials if necessary to keep conditions consistent. Next, the load cell provided slightly inconsistent results for our trial run. We will properly calibrate the load cell along with the VI to provide more accurate results during experimentation. Another problem we will face are temperature fluctuations, which could melt the ice, altering the friction values. To avoid this, we'll conduct the experiment in a temperature-controlled space, carefully monitor conditions, and document the temperature throughout testing. Uneven weight distribution in the bucket and the shoe could also introduce bias by shifting the weight. We will use controlled pouring techniques and fill each shoe evenly to minimize error. Finally, measurement errors may occur due to human factors or inconsistent instruments. To fix this, we will run multiple trials and average the results to improve precision and accuracy.